Morning, everybody. Nice to be here. Tomas O'Leary is my name. I'm going to talk to you about this tower that you see in the photograph here. Up to 2017, this was the tallest passive house building in the world. I'm glad to say it's no longer the tallest passive house building, which is great. There's a taller one in Bilbao at the moment, and there's a 56-story in the planning pipeline in Vancouver. So things are getting taller, much taller and taller as we speak. Our firm was established in 1993. We're an architectural firm, so we design passive house buildings exclusively, and we're also a training firm. So we do a lot of contractor coaching, architect training. We run the passive house designer program and so forth, and we've been doing that for a quarter of a century now. We have a lot of experience in low-rise social housing. This is a social housing local authority scheme that we've done in the southeast of Ireland, built at no extra cost. These houses are built in 13 weeks, and for most of those houses, the heating systems have never come on. They're so energy efficient. And this is another scheme that we've done in Dublin. Again, what we're finding now is the developers are actually getting on board, and the developers now see this as a kind of a prototype or a model that's appropriate for their business model. But what I'm really here to talk about is this Cornell Tech Tower. So it's a 26-story passive house student dormitory in Manhattan. It's a very iconic building. It's in the middle of Roosevelt Island in the East River, so it's in a very prominent location. The architects were Handel Architects, and the developers were Hudson and related. You can see everybody listed there on the right-hand side. So it's a 26-story building, 350 units. Some of these units are very, very small because it's a student dormitory, so you can imagine the accommodation in Manhattan per square foot is very expensive. So there's a good variety of sizes. There's an amenity floor at ground floor and also at the top floor, but otherwise in between they're all apartment studios and one bedroom. The 3-bedroom apartments are used by college staff. A lot of you will appreciate the key facets of Passive House. Passive House is really about, it's all about the envelope, have a good form factor to reduce the amount of exposed surfaces as much as possible, and I'll go through these factors in my presentation. Luckily enough, the island on which the building is built allowed for a southern orientation, so the widest axis, if you like, the front of the building faces south, and the east and west facades are quite narrow in width, so that's good because east and west present problems for overheating typically. If you think about the surface area of your own home, if you live in a single family home, you have 6 surfaces through which heat loss takes place, whereas in an apartment building, each home, if you like, has only one small surface area where you're losing heat. So it's far more effective, far more cheaper, in fact, far cheaper to build to the passive house standard with a big building than it is with a single family dwelling. And what we found actually is the insulation levels that you need in a tall residential building are actually less than you need for building code, which is kind of funny. So you get this incredible energy efficiency, superior air quality for actually a very, very kind of cost-effective envelope. So the U values that we used in the New York City building are on the left here, and the U values on the right-hand side are what we're going to need for NZEB, that's nearly zero energy buildings in Ireland, starting the day after Brexit. So we have Brexit, then we have NZEB, and then we have April Fool's Day, but we won't talk any more about that. But what's amazing, actually, if you look at the U value of the wall for the geeks in the audience, so the U value of the wall of this building is only 0.22, which is actually not a great U value, but it's enough to meet the passive house standard, so everybody's happy. And despite that U value, we've reduced the heating and cooling demand by 90% compared to a conventional building. It's in a really amazing location for a small firm from rural Ireland to be based, to be working on a project like this was really quite a thrill. And it's right beside the river crossing there in the East River, and if you ever go to New York, make sure you go and visit and sort of have a little nose around. I really encourage you to do that. As I said, it's part of a Cornell Tech campus, so there's quite a lot of buildings there, and this tower is probably the most energy efficient residential tower in North America by a long shot. It's probably the healthiest residential tower in North America as well, and by no question it's also probably the most comfortable. So do go and check it out. A lot of the envelope is essentially made off-site, made in Philadelphia, brought up by truck and then brought across the river by barge. So it's kind of like the most awkward situation you can imagine to pull a building together. And we were able to put up 6 of these panels in a day. And the panels came with the windows already fitted, the airtight tape already applied, the insulation already applied. So we weren't arriving, with 10 million bits that had to be assembled on site. Most of the envelope was kind of pre-assembled. The blue line that you see here is the weather-resistant barrier, so that's basically keeping the wind out and the water out. Our target for air changes per hour was 0.6. In reality, we got actually 0.15. So if you're interested in air changes per hour, that's the number we got. So it's like tight as a camel's ass in a sandstorm. It's unbelievably tight. One of the details that we like to apply here is the concrete column. So you see the column is set back 10 inches from the exterior envelope. And the reason for that is so a big burly New York builder can actually get his arms in there and his hands in there to zip it all up, because airtightness is a really key objective of this project. So rather than the columns being out on the edge of the floor slab, they were set back in, which allowed us to stitch these panels together. You can see the panels arriving here. We had this idea that the panels would be completely covered in this airtightness membrane, but then we realized that some guy has to weld these panels to the edge of the floor slab, otherwise they might fall off and kill passers-by. And a building shouldn't kill people. That's kind of number one. So welding, these membranes are good, but they can't survive being welded. So we basically had to leave out some of the membrane so we could do the welding after. And you can see on this photograph here on the right-hand side, you can see where we patched in later a piece of membrane over the bracket that was welded. So sometimes, despite your best plans and your best ideas to do everything off-site, when you arrive on site, it's like, what are we going to do here? You can see on the left-hand side here, those of you who have magnifying glasses or binoculars, you can see that the column is kind of set in from the edge of the floor slab to allow people to zip it all up. So if you're into Passivhaus, effectively we're building a submarine. And you don't want to be that person who is responsible for creating a leak in the submarine. So we have this total kind of red line on the warm side, on the vapor side of the building. And we did a lot of contractor coaching because the contractor had never built a Passivhaus project before. The architect had never done it before. The mechanical engineers had never done it before. So we basically wanted to make sure that we were going to get the airtightness level that we needed. In a tall project like this, you're fitting the kitchens on the ground floor when you're still putting up stud partitions on the 26th floor. So you don't get an opportunity to do a whole building a kind of a dress rehearsal airtightness test. So we have an air permeability. Now this is different than air changes per hour. This is permeability as opposed to air changes per hour. But in Ireland, so currently you won't go to jail if you end up at an air tightness of 7, which is effectively like sleeping outside. For NZ, we're going to go from 7 to 5. Whoop, whoop. Very exciting. If you're less than 3, you have to have mechanical ventilation system. And for the Cornell Tech building, we got around 0.58. So on permeability, we got 0.6, let's say, between friends. And on air changes per hour, we got 0.15. So it really, really is. I mean, ultimately, the air tightness number is the only real true testament of quality of workmanship on site. It's the one number that you can say, we made it. This is a finished look on the inside. It's always a bit of an anticlimax to visit a finished Passivhaus building because frankly there's nothing to see. It's just sheetrock and so forth. The fan coil unit that you see underneath the window there, that provides heating in the summer and cooling, it provides heating in the winter and cooling in the summer. There was quite a nice detail at ground floor level with a porch which has a cantilevered canopy, and actually there's a wonderful company here called Shock. You should go and visit them, and they make these wonderful details for having these kind of reduced thermal bridge connections. So we use this sort of a connector piece here. So everything basically is connected up, so we have a kind of a clean insulation line. And it was quite interesting. In North America, we're not used to using these materials. We're probably about 10 years behind in terms of supply chain. So all of these materials are kind of looked at with kind of great sense of mystique and mystery. So it's very funny, you know about the principles, you know about the theory, but to see it being applied to a massive building like this is really quite wonderful. We have this kind of love affair with glass. A lot of modern tall buildings are covered in glass, which is kind of immoral, really. We shouldn't be doing that. It's the height of arrogance to have a fully glazed building, and we really have to kind of move away from that. So this building sort of sets down a marker. About a quarter of the wall surface is window, and that's enough, frankly. That's about the right number, between 25 and maybe 30%. And so that's kind of an important message that I wanted to make today. The green line here is the air tightness line, and the bottom of the page is outside, the top of the page is inside. And basically everything is buttoned up. So as I said, we're making a submarine, and the hip bone has to be connected to the knee bone, and the knee bone connected to the ankle bone, and so on. It's basically simple. If you can wrap sandwiches or you can wrap a Christmas present, you can make a building airtight. It's just common sense, but it has to be done right. This is another view from the inside. So this is when you need to do your first air tightness test. You need to do the first the whole building air tightness test when everything is still exposed. I mean, you can see it. So if you need to carry out a repair. It's such a stunning building, and I had the great pleasure of visiting it last July when I was over in New York for a meeting, and it was great to be back there. The glass is pretty good in this building, 0.6 watts per meter squared Kelvin of U value, so that's really quite good. The frames are not great, I mean, by Passivhaus standards. That's not to take from the project. It's a fully certified, beautiful, high-performing building. But the supply chain for high-performance frames in the US 3 years ago basically wasn't there now. It is there now, but it wasn't there at the time. So the frames are not as good as the geeks in the room would be used to saying, but that's coming on. The solar heat gain coefficient is a very low number. You'll notice that. This is a very hot climate in July and August. You know well that New York is a very warm place. Normally, Passivhaus windows would have a solar factor of about 62. So in other words, 62% of the energy can make its way into the building. But that would have been too much for a building like this because we don't have any brise soleil, we have no external shades. So we effectively used a low solar heat gain glass, and we optimized that, as you can imagine. So it's not apparent from the outside. It doesn't have a reduced visible light transmittance, it just has a reduced solar gain. So that was kind of a very interesting thing to work on. The length of the window to wall connections is about 6 kilometers. So all the details add up. If you're talking about 6,000 meters of window to wall connection, you got to make sure, that that's really well done. In terms of mechanical systems, one of the main savings for mechanical systems like this is, one of the main savings for a project like this is on mechanical systems. And if you're reducing the heating and cooling demand by 90%, 90%, then you can actually jettison a lot of the heavy, bulky equipment that you normally need to compensate for a poor envelope, if that makes sense. So in terms of ventilation, this building is fully ventilated. There's about 16 air changes per day. So if you can imagine grabbing all the air in this building here now, right, and dumping it and refreshing it 16 times a day, that's what it's like to live in this building. So the air quality is extremely high. It's provided by only 4 ventilation units, and they're really quite modest in size. I mean, the main ventilation unit that's venting the apartments is about the size of a skip. Not one of those big low loaders, just kind of a normal skip you might have in your driveway this weekend. So it's really quite impressive how we can ventilate a building of this size for this kind of population because of how airtight the building is. Again, those of you who are really interested in the numbers, you'll be quite disappointed with the heat recovery efficiency of the ventilation units. Normally they're in the low 90s. In this case, they're kind of mid-60s, low 70s. And again, all this equipment was ordered and specified 3 and 4 years ago. And again, the supply chain is much more mature now. But even at that, so even with those frames which are not perfectly fantastic, and even with the low efficiency heat recovery ventilation systems, we can still meet the exemplary Passivhaus standard, which is kind of very good. So in terms of heating and cooling, as I said, every apartment has a fan coil unit underneath the window. It's very modest in size, and everybody can control the temperature in their space, so they can cool or heat. and that's done with an outdoor condenser unit. So in the lower left-hand corner here, the original design, that was supposed to be a viewing balcony back towards Manhattan, and I guess a smoking deck and whatever students do nowadays outdoors in student dorms. But actually we had to make that the plant room, if you like, the external plant room for the air-to-water condenser unit. So the students can't go out anymore, which is a bit of a pity for them. But anyway, so each second balcony, so one balcony, one unit on a balcony does 2 north faces, and the next balcony up does 2 south faces, and north and south, because half of this building could be heating while the other half is in cooling mode, if you can imagine, because it's in a kind of a north-south axis. So, like, incredibly simple technology, simple insulation, like rock wool insulation, tapes, membranes and all that. And it was really quite an amazing achievement for a team that had never done a building like this before, and we were very proud to be involved in this. We don't have very many tall buildings in Ireland, so I kind of said, right, I wonder how tall is the Cornell Tower compared to what we've got over in Ireland. So at one stage this was the tallest building in Ireland, and so nowadays we do have one taller building, which is in Northern Ireland, the Obil Tower in Belfast. So I think it's a really good story. This project was built on budget. It wasn't intended to be a passive house building in the very beginning, and so it's kind of it's nice that it turned out to be a certified passive house building on budget. We were very lucky to be involved in that project. We trained the architect, we trained the contractors, we did all the thermal bridge modelling, we did the PHPP model. And if there's anybody in the room here who's involved in a tall building or would like to collaborate on a large project, residential or commercial, we'd love to hear from you. So I hope I'm finished on time, John, and I look forward to hearing the other presenters as well. Thank you very much.